Yeah, thank you so much for joining my session. Today we are going to talk about building a minimalistic open lake house. So this session is pretty much a beginner-friendly session, and if you have been hearing about lake houses and all the jargons and technologies, the whole idea is to go beyond these jargons and hype and see how we can technically join different technical components together and form a lake house. I do have a Jupyter notebook that's up and running, so I'm hoping to be able to show some demos, but you know how demos are. I tested out just a few minutes back, didn't work out, but yeah, hopefully we'll have something to show. But if not, I do have a Docker image with all the things that I wanted to show. It's up and running, so pretty easy to pull it up, and for folks who are getting started into the world of lakehouses, super easy to try out as well. So having said that, let's give a brief introduction to me. I'm a developer advocate here at Dremio, and I currently focus on open source projects like Apache Spark, Apache Iceberg, Project Nessie, Apache Arrow as well. And I'm basically, my background is into BI and data science and data infrastructure. And over the years, I've been focusing on data infrastructure part lately. I'm also co-authoring the first book on Apache Iceberg. It's called Apache Iceberg, the Definitive Guide. So it's my first book as well, so it's pretty exciting in that sense. So yeah, let's get started. So in terms of the agenda, we will first start with the evolution of data architecture. We'll see how architectures have evolved throughout the years. It might be a kind of a known thing for a couple of you because you might have worked in this space for long. But again, next we'll go and start with the components of an open lakehouse. We'll really break it down and see what the components can be involved in a lakehouse. And then we'll understand how each of these components work and the architecture-wise of Iceberg. And in the end, I'm going to do like a demo of it and hopefully be able to show. One of the core things, again, from this presentation is that I'm going to use a catalog that's called Project Nessie. That's a very interesting project as well. It's like Git-like semantics for the world of data. So that might be super interesting to see in action as well. So obviously, over the years, organizations have been trying to build reliable and centralized data platforms. So the whole idea was that if they could democratize data, and that way the data consumers like data analysts or data scientists, they can use the data to build their analytical workloads on top of it, whether it's BI, machine learning, streaming, whatever it is. And then, data warehouses were kind of the first one, right? They enabled that, like kind of a centralized repository. So you pretty much, put data in a structured form, and then you can run your BI and reporting on top of that. But again, data warehouses had certain limitation in terms of structured data. We are trying to address a few of them with newer cloud data warehouses, for example. But again, there is a problem with running multiple applications and a cost factor as well. That is also a whole idea. And also, like data warehouse architecture, it kind of locks you to more of a closed architecture where you really have to depend on their own stable format and own file format to run your analytical applications. So then came the era of data lakes. With the Hadoop, we are already aware of the world of big data and just trying to understand what Hadoop was. A lot of tools, a lot of technologies in that era and space. But ultimately with Hadoop, we came up with like Hive and those kind of technologies that kind of provided an abstraction on top of a file system like HDFS. So data lakes were great. Organization could basically dump any kind of organizational data, operational data that they had into a data lake, and then didn't really have to worry about structure, unstructured, and they can, depending on the use cases, they can leverage it for, their use case. But there were a couple of problems, and I think it might be better to look at that so that we get a context of why lakehouse. So one of them was that obviously you need some kind of an abstraction. So with a data lake, you just can't just dump all of your data and let your analysts and scientists be able to deal with the physical bytes and bits of the data. And most importantly, what lacked in a data lake was those kind of transactional guarantees. So you might have some kind of Parquet files in a S3 bucket, and you want to do some transaction using query engine. You're good to do that, but you don't know what will happen when concurrent writes happen, multiple writers are writing at the same time. So yeah, those were kind of the main kind of problems. And also, like with the data lake, there's hardly any quality and governance around the data. So really, it's more of like, how do you really build a machine learning model or like a, BI report if you don't really have, quality data to use that. So that gave rise to a new kind of architectural platform called Lakehouse, and as you can probably guess, and it's a Lakehouse conference, so it's the best of the both world kind of. So your data is, the whole idea is that your data is stored in open kind of data architecture, and then you open up your data architecture to other compute engines depending on your workload, whether it's streaming, machine learning, or BI. So This is one of the like the slides that I kind of like always like to think visually, and like it helps in terms of the perspective as well. So what really makes up a lake house, right? So in terms of the components of a lake house, there are as you can see, there are a couple of technical components, and I'll start from the the bottom part to the top part. So in the extreme bottom part, we have the data lake storage, which is basically your any kind of like a data lake system, a file system or object store like S3, ADLS. And then there is, it can also be like a Hadoop file system as well. And on top of the data lake storage, you have the actual file formats, the files, right? And that's where your data is organized in a way, for example, either row fashion or columnar fashion. So things like Parquet, CSV common, JSON-wise, that basically lands in that particular data lake storage. And on top of the file formats, we actually have something called the table format, and that basically opens up the Lakehouse architecture. So all those transactional guarantees and all those operations that I'm going to talk about is going to focus a lot on the table format. So obviously, like the table format, the whole idea, just to give a gist of a table format, is that you organize those files in the form of a table, so that you have some kind of like a schema towards that, and you're able to, as an engine, you're able to leverage that particular table format specification to, do whatever you want to do with the data, whether processing, transformation, and those kind of stuff. So Apache Iceberg, Delta Lake, Hoodie, three common table formats right now. But again, this table format is not something new. We have had the Hive table format in the big data world. So that basically led us to today's, file formats. We saw a couple of caveats. Specifically, Iceberg came out of Netflix's engineering team. They were using Hive, and they realized there were a problem with scaling and being able to not leverage statistical information for optimization and stuff. So that's our table format, and that's one of the main components we are going to talk about. And on top of that, I have the Lakehouse catalog. That's basically it's a metadata store for all the information that we want in our table. So all the namespaces, all the table information. And that basically helps all the engine to basically come to the catalog and lets you access all the data that's in our storage. And again, on top of that, so in terms of the catalog, there are a couple of options. I'm going to specifically talk in terms of Iceberg, because Iceberg needs a catalog for concurrent writes and stuff. So there are things like AWS Glue, Nessie is an open source one that we're going to talk about, but obviously Hive Metastore is something very commonly used as well. And on top of that, we have the compute engine. So like I said, all this catalog metastore, the open table format, and the file format, that part, since it's not unified into a single structure, that's why your data is open, and that's why it's accessible to all these different engines that you see. So for example, if your use cases like distributed ETL, Spark could be an option, streaming like Flink or like Trino or Dremio, those could be an option as well. And obviously, we have our users and application on top of that, and they'd be accessing this data using interfaces and protocols like ODBC or like Apache Arrow and Apache Arrow Flight SQL as well for faster performance and stuff. I'm going to focus, just to give an idea about the catalog, I'm going to focus on the Nessie, and then I'm going to focus on Iceberg and see how we can leverage Spark as the compute engine for that. So just to give a more detailed idea about the table format, I talked a bit about it, but what is a table format? Like, it's not something new. Obviously, with the databases, we have seen the concept of tables. It's a way to organize the files in the form of a particular table. And that's how you open up your table to different engines. So in the big data world, obviously, like I said, with Hive, we have had some kind of an abstraction, right? At least with the Hive table format, like, we were able to use something like HiveQL, which is kind of similar to SQL, and that way analysts could use that particular language to access the data instead of running all those MapReduce jobs, and it's getting super cumbersome as well. So the only difference between something like a Hive and Iceberg table format, and that's the kind of the core kind of design difference, is that in Hive, everything was organized in the form of a directory, and inside those directories, you have those files, right? Whereas in Iceberg, a table is a list of a canonical files. Basically, all the files organizes them in the form of a table. So that's the core difference. So as you can see here in the image, like this is more of a high-level architecture of Iceberg, just to get an understanding of it. So there are three layers. One is the catalog layer, one is the metadata layer, and there is the data layer. So catalog layer, we talked a bit about it. It's how you basically, that's the first place in the Iceberg world where you'd come and say, hey, you know what? Give me the latest metadata file, which has all the information with all that lineage that you see in that particular tree form structure up to the data files. So catalog is that place. So for example, if you have a SQL query, say like something from this particular table, you will go to the catalog and ask for the latest set of metadata file. And the reason you always ask for the latest metadata file is because you always want the fresh set of records, right? Irrespective of the engines, you really want to be able to get the fresh set of records for your users. So that's the catalog part. And every time a write operation is done by an engine like Spark, it will have to write out, it basically writes out a new metadata file, and that metadata file is atomically swapped in this particular catalog. So technically, the only condition for something like a catalog to be a catalog is that it can be like a database or a data store that has some kind of a locking mechanism for that kind of swapping. So that's the prime condition to be a catalog. The next component, if you come from the catalog, you'll get the location of the latest metadata file. So let's say in this particular example, this is the version 2. Let's say there's a metadata file. So that's the second component. That's another component of a metadata. And that has information about the schema of the table, the partitioning scheme, and all the valuable information that you might expect from a table format. And from the metadata file, you have a manifest list. And I'm going to give a primer about why do you need these 3 different components. So the metadata manifest list is basically, it's kind of an index, and that's kind of like acting as kind of an index for things like partition pruning and stuff. So you are able to control the manifest files using those manifest lists. And the manifest files are actually the one who are tracking at a lower level. They're tracking those data files, the Parquet and orgs. So manifest file, one of the other important use case of manifest file is that it also has those statistical information from Parquet, right? From all those metadata information from Parquet, it goes and rewrites them in the form of a manifest file. So all the upper and lower value bounds of a column, null value counts, and those kind of stuff you can easily get, and then you can use it for pruning purposes. So inside the metadata, we have the metadata file itself, the manifest list, and the manifest file. And finally, the data layer is the end, which basically all our data files. So moving on from the table format, another important component is obviously the compute. We need the compute part of this. We have the data that's stored openly. So that's the best benefit, your data is open, so you can use any kind of compute engine. But having said that, Apache Spark is one of the most, feature-rich compute engine. I work on the community part of it, so the community has been really working on, improvising and adding new functionalities to Spark, even with the latest release. So that Spark is super important to the community. If you're looking for some kind of a way to get started, that would be my go-to solution as well. But again, there are a couple of other options, for example, my company Dremio that works for a compute part as well, and there is Fling and Trino and other options as well. And what can you do using Spark? Well, technically, a lot of stuff DDLs, whether it's creating tables or even reads, writes, inserts and updates and deletes, upserts. Even structured streaming is supported to some extent, so that's something interesting as well. Again, there are also latest community improvement in terms of the for example, things like CDC. Now you can basically natively call a Spark procedure, and you can track those changes in Iceberg table, and you can use those tracking changes to be pushed to the downstream real-time applications, for example. So yeah, that's something super interesting as well. Okay, so now coming to catalogs and Nessie, right? So we discussed what a Lakehouse catalog is. We understand that it's a place where you go for the latest metadata file, and that kind of brings those transactional guarantees to the world of Iceberg, and in general, Lakehouses. So Nessie is basically a transactional catalog. Nessie is to data lake what Git is kind of to code repo. So the whole idea is that you are able to basically do things like in the world of software engineering. So for example, in the software engineering world, you have your main production branch, and as a software engineer, you go and create a fork of that particular branch, and you work in your local branch. You develop some new features in that branch, and when you're done, you merge that particular branch to production, right? To the main, and based on a code review and stuff. So the idea is kind of same, that you put catalog and you basically fork make a zero-copy version of the table. So when you say create a branch, this particular dev branch in Nessie, it creates a no-copy version of the table from that local, high-level topper data lake format, which is Iceberg. So basically, you will have your own local environment, and you can run your distributed, whatever, ETL or data quality checks. We have also seen people use it for machine learning-based experimentations, where they have to basically, have to have their own environment, so that it doesn't really impact anything on the production side of data. So that is something that Nessie brings to the table. Again, there are other things like data versioning and ability to track the commits, so you can use that to roll back tables and stuff. So that's what Nessie is all about. But we obviously, in terms of the workability with other table formats like Delta, Nessie, we have tested Nessie that worked with Delta, Lake open source part. At some point of time, we are working with Databricks to like see if we can, move the PR now to work it with like the latest version of Delta Lake. So that's super interesting as well. But we do have a couple of tutorials on how to use Delta Lake and Nessie, so I might be able to share that as well. But again, you are not limited to a particular particular catalog in this particular architecture, right? So whether it's a Hive Metastore, whether you want to use something like AWS Glue, the choice is yours. You can bring your own catalog. But specifically for this particular talk, we are going to focus on Nessie and see how it kind of brings those abilities with Git. So this is another example of like how Nessie works. Like, you create a branch, you run your Kafka injection, and you basically do a transformation. When you're done, you merge that branch to production. Just a snippet of, just to give an idea of how Nessie works. And it's also a version control, like I said, so you can refer to a particular, so you can really like when you're, for example, like you have done some kind of a ETL ingestion, and you create a tag of that particular version of data. And you basically refer to that particular tagged version of data for your analysis, for your dashboard, or for your, for example, for machine learning, reproducibility is a great use case of that. Like you can reproduce model by referencing that particular tagged version of data. So it's similar to the world of Git, right, where we had kind of like committed tags and those kind of things. Okay, so up until this point, we have a fair idea of what Lakehouse is, just the technical component of Lakehouse, and we understand that, the data part, the top file format, the table format, and the catalog really opens up that openness part of a Lakehouse. So how do we really build a Lakehouse, So, the whole idea is to just bring these different components together and, bring it to a form. So that they can all communicate with each other. So it's Nessie, it's Iceberg, and Spark that are going to communicate. And we are going to see how we're going to do that using PySpark. So yeah, so this is not the Lakehouse that we're going to build. We have something on the left that we are going to like focus on. Just to give a visual picture, we have some data. I have some CSV file in a in a S3 bucket. I'm going to just use that to load it in my Iceberg table. Basically create a table using Spark around that particular CSV file, and see how we are being able to like do reads and inserts and those kind of stuff. And then we have the catalog, like I said, that will bring all those capabilities with like versioning and like branching and tagging. So configuration again. Hopefully this is not overwhelming. This is straight from my Jupyter notebook, but the whole idea is that you're bringing all these components together. So it's pretty much boilerplate stuff. Again, nothing complicated. Like you have the Iceberg Spark runtime that's already available. You have the Nessie Spark extension that is already available. You just pull it up in a configuration, and then you create a catalog and say, okay, it's a Nessie catalog, and then let Spark know that it's a custom catalog, because by default Spark comes with like I think the Hive or Hadoop catalog. So you want to make sure that it's a custom catalog, and then you give a warehouse location. That's the location where my compute engine Spark in this case is going to write all the files and do all the operations over there. And I also have the Nessie URI. Basically, I have Nessie up and running here in my system locally. So I'm going to use that particular URI to use it in my configuration. And finally, we have a couple of Spark SQL extension. Again, boilerplate stuff. But yeah, that's how you bring all the configuration together. Okay, so to get started, our first step obviously would be to first create an Iceberg table based on the CSV file that I was talking about that's in my S3 bucket. But before we do that, we want to leverage the branching capability that I've been talking about with Nessie, right? So with Nessie, like I said, you can create a local development branch, and we are going to do all our operations that in this particular discussion in that branch, so that we kind of mimic that scenario where we are not impacting anything on the main branch. That is, the production data still remain untouched. So we're going to create a branch of that, and then we are going to start our creation of the table. So to create a branch, you can just say just create branch that. I can also show it over here, and hopefully I'll be able to do that. So let's say create branch demo in Nessie, and once you do that, a new branch is created with a new hash code. That's the hash, that's internally Nessie's tracking all those commit using those hashes. And I can also check all the branches that are there in my data lake, right? So you can just see a list of references in this particular catalog, and it will basically pull up all the branches that I have. And I have a couple of branch here, main, dev, stage, ETL test, and stuff. So I'm going to use the demo branch for this particular demo. And so basically, by default, you are in the main branch when you start up your environment. So all you have to do is when you have to switch that particular branch to something else, you're going to say use reference demo in Nessie. And that's going to switch it from the main branch, and now we are in the demo branch. So we can do everything in that branch. All right. So now let's go ahead and create our first Iceberg table. And it's, again, a simple create statement. Iceberg is pretty much native SQL experience, so just go ahead and create the table. I'm going to create a table in this and just say give it a couple of column names. And once I do that, one interesting thing that I want to show and just be able to so that you can follow along with the architecture that I kind of talked about in the very beginning is what happens underneath when we run a create statement. So that can be super helpful in terms of understanding like debugging things and stuff. So when we created ran this particular create statement, in my S3 bucket, I'm going to have a folder called metadata, and that folder is going to have my first metadata file because this is a detailed operation that I ran. So I'm going to have a metadata.json file over there, and that metadata file is going to be able to pull up all the information on my table, right? So let me just show you how a metadata file looks like. So this is what a typical metadata file would look like. It might be a bit smaller for the audience, but yeah, in general, there is the schema, there is this partitioning scheme. I haven't really used any partition here, but there is the schema, the partitioning scheme. There are things like the current snapshot ID and all those information that are accumulated in a metadata file. So once we're done with the metadata file, I'm going to come here. So as of now, the whole reason we don't have, by default, we should have a folder called data. But since we just created a table, we haven't inserted any real data files. So that's why we just see only the metadata file. So in terms of the architecture and how we kind of like saw from in the previous slides, so on the left-hand side, I'm going to show the file system. And on the right-hand side, I have the architecture. So how it looks like when you create when you run that particular statement is that Iceberg goes ahead and the compute engine Spark, it writes that first metadata file as I explained it in the previous slide. And that's my current metadata file. Like that's the latest file. So any kind of engine that comes to Iceberg and says, hey, give me the latest data, so it will give based on this particular point of time, which at this point of time, there is no data, obviously, it's just a simple table. So now, again, going back to like inserts, that will be our next step. So we want to insert some record, and like I said, I have some kind of data on my S3 bucket. I'm going to just use that. I'm creating a temporary view on the Spark session, but again, that's up to you. But yeah, hopefully we'll have this particular data in this particular table. So just say insert into this table, and then I'm selecting it from that particular view. So while we have the data inserted, let's go and check. Okay, we already have the inserted data. So now if I run that particular query, it'll give me all the inserted records that we have. But the most important thing would be to understand how we are basically seeing this thing architecturally and what happens in the architecture when we kind of ran this insert statement. So when we ran this particular insert statement, like I said, now we have two folders. One is the metadata folder, and other is the data folder. So now the metadata folder, again, has the new metadata file because it was a new write operation. There is a manifest list that just got created because it's the first operation, and then there is a manifest file as well. So all those three metadata files are there. But also in the data file, we have a Parquet. So Iceberg went and wrote that data file as Parquet file. So that's the two folders that we have right now as of now. And in terms of what happened under the hood, so when we ran this particular statement, so Iceberg went ahead and said, basically the write operation goes from the down to the bottom part. So as a compute engine, Spark basically had information about the data files. It went and wrote ahead in the data file. And it uses those Parquet information, like I said, to write those upper and lower value bounds and those kind of statistical information on a manifest file. And from the manifest file, it's being tracked to the manifest list. And finally, it goes and says, OK, this is the current metadata file. And now this new metadata file needs to be updated in the catalog because that's how you're going to have that atomic swap, and that's how any new engine that comes into the picture, they're going to access data from the catalog, and they're going to be able to access the fresh set of inserted records that we just did. So that's what basically happens. The catalog is now referenced with in the swap with the new metadata file, and Spark as a compute engine does that. All right, so now that we have our table created, we saw how a read, basically it's a read operation, but just to give an idea of how read works, in terms of read, like I was explaining, let's go and check this particular slide. When we have that particular query, Iceberg will say, hey, go to the catalog and says, give me the latest metadata file. So in this case, that's the second metadata file because the first one was from the create statement. So now we have the second metadata file as the metadata file, the version 2. And from there, you get the latest snapshot. And snapshot in Iceberg world is basically any kind of write operation that you do, it's tracked as a snapshot. So I think in the Delta world, it's kind of like the change log or those kind of information where you're kind of tracking those changes. So you have that particular information as a snapshot. So in the metadata file, you go and look for the current snapshot ID. So if I have to go and show you the metadata file, this is my second metadata file. Here I have a field called the current snapshot ID. And this is basically the latest snapshot, the latest operation that ran. And I'm going to use this particular metadata file, current snapshot ID information to find my manifest list, which is in this particular location. So if I go back here, and I go back here and I see the current snapshot. From that, I'll be able to get the manifest list, and from the manifest list, I will be able to get my manifest file and the actual set of file. So whatever was specified in my query, whatever filter was there, it will be able to, if there was any partition or any kind of strategies around them, it will be able to pick that particular file from that particular location. So this is how basically a read works under the hood. And the last one is obviously the update operation. So in general, there are two strategies for updates in Iceberg. One is copy on write, which just to give a high-level idea, and I'm not going to go deep on these strategies today, but the copy on write is basically really good for the read side kind of like throughput. So when you have like a lot of like a read happening, you might want to like apply something like a copy on write. But when there are like streaming data and a lot of frequent updates, merge on read is a new strategy that was added. So that might be really helpful for those kind of like applications as well. So with copy on write, you are actually basically rewriting those data files, and that's why basically the overload is on the right side. Whereas on a merge on read, there is no rewrite. You are basically reapplying those changes, and that's how there is no overhead on the right side. Okay, so with which branch did we write to? So as of now, we were in this particular environment, and we had we were working in a particular branch. So as you can see, on my Nessie server, if I go and reload this particular URL, I have a couple of branches here. I was in the demo branch, and I can see my my sales table and all the metadata information in Nessie. Whereas if I go to my main branch, I don't see any information, right? Because all that I did was I did in my demo branch, and I didn't really run anything in my main branch yet. So yeah, so we are currently in the dev branch. So we are still to switch to the main branch if we want to merge it to the production environment. But before we go that, I can just show you as well how to do that. So one way to do that is that you basically run this particular command. Just say, hey, merge this particular branch demo into main. And once you do that, all this table and all the information that you had on the dev branch will finally be merged to the main branch, and it's made available to all the production workloads and users. So metadata table is another thing that I wanted to cover today. Metadata table is also very interesting. Like, it's not only important to Iceberg, but also other table formats like Delta and Hoodie as well. Metadata is really the core to this table format. We want to be able to not touch as less data files as possible, and we want to be able to leverage on the data, our metadata information, for certain things, right? So for example, there might be information like how many small files are there in my data lake, right? Which partition was the last one that was updated. So you really want to be able to access this information, and Iceberg makes it super easy to access this information via system tables. So you can either use Spark SQL or data frames to read these tables and get information on the overall health and the overall, basically the environment of the, the tables and the lakehouse. So things like, data files, history of the table, did I really roll back some tables? Those kind of historical information are also very critical. How many snapshots are there? Do I really need that many snapshots? Because over a period of time, you're going to end up with a lot of metadata files. So your organization might have some kind of a maintenance strategy that you're going to run like a job, a Spark procedure or something to compact those files and, expire those metadata files. So here is, again, some practical examples just to show, what information is captured in a metadata file. For example, the history table has information on, what time a snapshot was committed to, was it something that was rolled back? Was it a native table? Things like what operation happened, whether it's an append or whether it's an insert or whatever it is. And those kind of information you can easily find from the metadata tables. Time travel, another important concept that we come from the data warehousing and databases world. We want to roll back in time and go back in time and understand, probably do some analysis. And for example, things like end of quarter analysis, end of financial year analysis, you might have specifically tagged data that you want to refer back now. So Iceberg allows you to do that. Other table formats also does that. But it's a very easy way to do that. And like I said, in Iceberg, everything is a snapshot. So you're basically looking at a particular name reference in the point of time. So that's basically the use case. And you can use either the snapshot ID or the committed timestamp to basically roll back your tables. OK, so we have adopted, let's say, a data lake table format, whether it's Delta, Iceberg, whatever it is, it's operational. You're able to ingest new data on your data lake, and you're able to run your analytical applications on top of it. And everything is going great, right? Your data architecture is pretty much open. It's not limited to a particular compute engine. But the problem is your query patterns may change. You might have new query patterns added. And over time, as you get more and more data, you might have small files and those kind of things. So you might be able to, you might want to expire those things, and you might want to be able to manage the metadata. So that is another critical aspect that is super important with the Lakehouse architecture, with the table format, which is a metadata layer. So there are things like compaction, hidden partitioning is super important as well. So for example, like in the Hive world, coming from the Hive table format world, with partitions, you would have to add a separate column into the table. And really, since everything is in a directory-based structure in Hive, as an analyst, as a user, I don't really need to worry about the physical layout of the table, right? And say, hey, let's say if your table is partitioned by date, and if you're querying using a timestamp, you basically have to, do this conversion at that kind of physical layer rather than at the logical level, right? So that's the whole difference that comes with Iceberg, and hidden partitioning is a great example of that. So with Iceberg, irrespective of whatever partitioning scheme you have defined, for things like if you have for example, if you partition by date and you are querying by timestamp, Iceberg internally will do that kind of transformation, and that's why it's called hidden, because you don't really need to worry about it. So as a user, I don't need to worry about the physical layer. And then there are things like partition filtering, like for example with the statistical information, like I said. With Iceberg, you can also use this for example, stochastic skimming algorithm sketches. So those are basically approximation kind of thing where you can really use for optimization and stuff. So that is also incorporated. And then we have things like sorting and Z ordering and multi-dimension clustering and stuff. And the best part is all of these things are pretty much only accessible via Spark, because the community is open and really opens up the scope for all the engineers to implement this thing. So all this expiring snapshot, removing metadata files, compacting data files, or deleting orphan files, all these operations can be done using Spark procedures, and they are already very operational. Okay, so like I said, we were in the dev branch, and the only way you can merge it to the main branch is say just merge branch demo. Either you can merge this particular branch, or also you have the option just to drop the branch. And because specifically what we have realized with our customers is that they'll be typically using it for their ML experiments. So after a particular experiment is done, they're going to just drop that particular branch because it's a zero copy operation. There is no overhead of copying data and stuff. So that's super helpful as well. So I can just say merge this particular branch, and once I do that, that particular branch will be available in production in the main fork, and I can now see the sales table that's there in the main branch now.